Hello everyone, my name is Junaid Dialis and my student number is 2544593. This video presentation is for a module called Distributed Service Architecture at the University of Bedfordshire. For this assignment, I developed a game called Beat the Count using the Hard Game API given by the university. This is an interactive web-based game where players are shown an image with multiple hearts along with the statement. The system is built using a React frontend, Django backend, and MySQL database, and it also integrates with an external API to generate puzzles. Let's move on to the game. So here now I'm in the login page. If a user doesn't have an account, they can register to the system by clicking on the registration option. So now I'm going to create an account by entering the username and a password. After confirming the password, I submit the registration form. As you can see, the user is successfully registered and redirected to the home page. On this page, you can see the user profile. And on the right side, there is a leaderboard showing top scores based on the difficulty. At this point, the user's current high score is 0 since this is a new account. Now I'll click the play button to start the game. Here the system shows the difficulty selection page. As you can see, there are three options: easy mode with 10 seconds, intermediate mode with 8 seconds, and hard mode with 5 seconds. I briefly navigate through the options and now I'll select easy mode for demonstration. Now the game starts. In this first puzzle, there is one heart on the screen, but the statement says there are 9 hearts. So I select false, which is the correct answer, and the score increases by 1. You can also see that the best score is displayed next to the current score. Moving to the next puzzle. There are 2 hearts, and the statement says there are 5 hearts. Again, I select the false, and the score increases. Let's keep going. Now I will demonstrate what happens when the user selects the incorrect answer. In this next puzzle, I intentionally choose the wrong answer. As you can see, one life is reduced. Initially, the player has 3 lives, and now it drops to 2. In the next puzzle, I again choose the wrong answer, and another life is reduced, leaving only 1 life. For the next round, I wait until the timer runs out. As you can see, when the countdown finishes without an answer, a life is still deducted. Now the game is over. Here you can see the game over screen, which shows the current score and options such as play again and main menu. Now I'll go back to the main menu. As you can see, the user's high score has now been updated from 0 to 5. This shows that the system stores and updates user progress correctly. Now I'll log out from this account. Back on the login page. Next, I will move on to the explaining the code structure of the system. So this is my project structure. As you can see, I have clearly separated my front-end and back-end components. This separation helps achieve high cohesion and low coupling, because each part of the system has a specific responsibility and they communicate through well-defined interfaces. I chose this architecture instead of monolithic approach because it improves scalability and maintainability. So starting from index.html, this is the entry point of my application. Main.jsx. The React application is initialized and rendered. Now I'm in the app.jsx, which is responsible for routing and authentication logic in my application. Here I manage the application state, including the current user and loading status. This allows the system to track whether the user is authenticated, which is a part of virtual identity. In this use effect hook, the system checks if a user session already exists when the application loads. The getUserInfo function communicates with the backend to verify the session. While the session is being checked, the system displays a loading state to improve the user experience. Here I use browser router to manage navigation within the application, and all application routes are defined here. These are public routes such as login and registration. Here I implemented protected routes. If the user is authenticated, they can access the home page. Otherwise, they are redirected to the login. This is how virtual identity is enforced in my system using session-based authentication. This route dynamically passes the difficulty level to the game component, making the system more flexible. This fallback route ensures that invalid URLs are redirected correctly. So overall, this component demonstrates high cohesion because it focuses only on routing and low coupling, because it is independent from UI and backend logic. Now I'm showing you API.js. which centralizes all communications between the front-end and back-end. Here the base API URL is defined, making the system easier to maintain. This reusable request function handles all HTTP communication with the backend. By centralizing requests, I reduce duplicate and improve maintainability. An alternative would be making API calls directly inside components, but that would increase coupling. So I centralize them in this file. This function manage authentication, demonstrating virtual identity. This function fetches the game puzzles from the backend. This sends user answers to the backend for verification. This updates the user score in the database. These functions show interoperability between the front-end and back-end system. This retrieves leaderboard data from backend. Overall, this file demonstrates low coupling because UI components do not directly handle HTTP requests. Here you can see the user's username and high score being displayed. This demonstrates virtual identity because each user has their own stored data retrieved from the database. Here the system fetches leaderboard data from the backend using an API call. This demonstrates interoperability between the frontend and backend using HTTP and JSON. I chose to fetch this data when the component loads to ensure real-time updates. This function is triggered when the user clicks the logout button. It sends a request to the backend to end the session. This is an example of event-driven programming, where user action triggers system behavior. Here clicking the play button triggers navigation to the level selection page. This is another example of event-driven programming. Here, the difficulty levels and timers are defined, such as easy, intermediate, and hard. This keeps configuration separate from logic. When a user selects a difficulty, an event is triggered, and the value is passed to the game. This is the core game component where all gameplay logic is implemented. Here the game fetches puzzles data from the backend. This demonstrates interoperability between the front end and backend and external API. I chose to handle this through the backend to keep the correct answer hidden for security. Here I use set interval to implement the countdown timer. This is a time-based event demonstrating event-driven programming. When the timer reaches 0, it automatically triggers a function to handle the timeout. This shows how the system reacts to the event rather than running sequentially. This function is triggered when the user clicks true or false. The answer is set to the backend for validation, demonstrating interoperability again. The score is updated and stored in the database. This demonstrates virtual identity because user's progress is persisted. These buttons trigger the handle answer function when clicked. This is a clear example of event-driven programming where users' actions trigger system behavior. When the player loses all lives, the game ends and the final score is saved. The system updates the database with the user's score. The retry button allows the users to restart the game, which is another event-driven programming. So overall, this component demonstrates high cohesion while integrating event-driven programming and interoperability. This file handles backend API endpoints where each function responds to requests from the frontend. This handles authentication and creates user session. Here the backend sends a HTTP request to the external heart API to fetch the puzzle's image. Here the correct answer is stored in the session. Only the image is sent to the frontend. I chose this approach to prevent cheating and improve security. This triggered when the user submits an answer, demonstrating event-driven programming. This retrieves the correct answer stored in the session. Then it checks whether the user's answer is correct. This is a clear example of event-driven programming because the system reacts to user input. This updates the user's score in the database, supporting virtual identity. This retrieves and sends data to the frontend, demonstrating interoperability. This retrieves the top players from the database. In here, the data is serialized and sent to the frontend. This model stores user data like high scores, linked to each user. In serializer PY, serializes validated input data. In URLs PY, it defines API endpoints. This endpoint connects to the external API, demonstrating interoperability. The settings PY configures database and front-end back-end communication. So overall, my system demonstrates software design principles through modular architecture, event-driven programming through user interactions and timers, interoperability through communications between multiple systems, and virtual identity through authentication and persistent user data. Thank you for watching.